keep making mistakes like that. I'm awful.
No, you're not.
And annoying.
You know what? You can't focus on what's going wrong. There's always a way to turn things around.
In this video we'll go over a sensitivity analysis problem where we change the right-hand sides of constraints. So here we are given a linear program and its optimal tableau, and there are several questions that we need to answer. So the first question is to find the dual optimal solution. We read the dual optimal solution in row 0 of our tableau in the columns corresponding to the slack variables. So y1 is gonna be the coefficient for s1 in row 0 and y2 is the coefficient for s2 in row 0. So we have 0 and 1 here. Then we need to determine the range of values for the right hand side b1 of the first constraint for which the current basis remains optimal. Alright, so when we change the right hand side, we need to recompute b inverse times b to determine the new values for the right hand side in our tableau after we made the change, right? So in the tableau corresponding to the same basis as in this tableau, but for the problem with the changed data. Now we can read b inverse from the optimal tableau. But here you need to pay attention to one little detail. Look at which order the rows are listed in this tableau. So if I write down the basic variables for each row, then we can see that the basic variable for row 1 is s1 and the basic variable for row 2 is x1. And you can see that these variables are listed in the order which is opposite to the order in which they're listed in the columns. So in the columns, x1 goes ahead of s1, and here s1 goes before x1. So as a result, when we look at the columns corresponding to these basic variables, they form a matrix given by 0, 1, 1, 0. Alright, so you have the column for x1 here, the column for s1 here. So when we juxtapose the columns, this is the matrix that we're gonna get. But in order to have b inverse in the columns corresponding to the slack variables, we need to make sure that the columns corresponding to the basis form the identity matrix, not a matrix like this, right? So because by Gauss-Jordan rule, what do? First, we add the identity matrix to the right of our matrix, and then we do elementary row operations to transform the initial matrix for which we look for the inverse into the identity matrix. And as things are in this tableau, we transformed the matrix B into this matrix right here. We need to make the swap of the rows to transform this matrix into the identity matrix. So therefore, what we need to do, we need to swap the rows of our tableau in order to be able to read b inverse from the columns corresponding to the slack variables. Alright, so when I write b inverse, I need to reverse the order of rows. So b inverse is gonna be 0, 1/3. So first I write this row right here, and then the second row is going to be 1, -2/3. And now when I compute b inverse times b, our b is modified to 8 plus delta 10. So we are modifying the right hand side of the first constraint first. So now b inverse times b becomes 0, 1/3, 1, -2/3 multiplied by 8 plus delta 10. And when we multiply, we obtain 10/3 for the first entry, and then delta plus 4/3 for the second entry. So now we need to make sure that this is greater than or equal to 0 for feasibility, and the first entry here is a constant, it doesn't depend on delta, so we only have one inequality to solve. So delta plus 4/3 is greater than or equal to 0. This means that delta is greater than or equal to negative 4/3. So to determine the range for B1, we need to add the range that we got for delta to the current value of B1, which is 8. So it's going to be 8 minus 4/3 is the lower bound, 20/3, and plus infinity is the upper bound. Alright, so the answer for this part is going to be 20/3 to plus infinity. So this was for part B. Then for part C, we need to determine the range of values for the right hand side B2 of the second constraint for which the current basis remains optimal. So in this case, instead of 8 plus delta for the first entry, we'll have 10 plus delta for the second. And we have B becomes 8, 10 plus delta. And then B inverse times B is going to be 0, 1/3, 1, negative 2/3, 8, 10 plus delta. This is equal to 10 plus delta over 3 for the first entry. And then 8 minus 20 plus 2 delta over 3 for the second entry. Which is the same as 10 plus delta over 3. And 4 minus 2 delta over 3 for the second entry. And again, this needs to be greater than or equal to 0. And in order for both of these to be greater than or equal to 0, delta needs to be greater than or equal to negative 10 from the first inequality and less than or equal to 2 from the second inequality. So and then B2 needs to be added to this range in order to obtain the range for B2. So we have 10 minus 10 is 0. And 10 plus 2 is 12. So B2 must be between 0 and 12. And we obtain this range here. This is our answer for part C. Then the part D asks to change the right hand side of the first constraint to 7 and to get the new optimal solution. So for part D we will use the data from part B because this is where we computed the new optimal solution after we changed the right hand side of the first constraint. So the new optimal solution is given by this vector, and in this vector this entry corresponds to the variable x1 and this entry corresponds to the variable s1, right? So because we follow the order in which the variables are listed in the columns and we swapped the rows accordingly, remember. To answer questions like this, we start by determining what's the delta, right? So what was the change to the right hand side? So we had 8 originally and now we changed it to 7. So 7 minus 8 is negative 1. So your delta was negative 1 and we see that it is greater than negative 4/3. So we are within the range, which means that all I need to do to obtain the new optimal solution, I just need to plug in negative 1 in here. As a result, for part D, our B inverse times B, which gives us the values for x1 and s1, will be given by 10/3 and negative 1 plus 4/3 is 1/3. That's the value for s1. But we only need to report the values for x1 and x2. So the value for x1 remains 10/3. The value for x2 remains 0 because x2 still remains the non-basic variable. We don't have to report the value for s1. Alright, so now finally for part E, we'll look at the change of the right hand side of the second constraint from 10 to 5. So this corresponds to delta given by negative 5. So for part E, you have delta given by 5 minus 10, which is negative 5. And the new optimal solution is going to be obtained by just plugging in delta equal to negative 5 into this expression for B inverse times B. Right? So we see that we are within the range. Delta equal to negative 5 is clearly greater than negative 10 and less than 2. So all I need to do is compute the new optimal solution. So x1 s1 is given by 10 minus 5 over 3 for x1, and then 4 plus 10 over 3 for s1. So for x1 we are getting 5/3, and for s1 14/3. So this is our answer. So we see that x2 still remains at 0 because it is still a non-basic variable, and the value for x1 is 5/3. So this completes the solution.